In 1881, the UK's first community electricity generator flickered to life in the small town of Godalming. Over the next few decades, the industry slowly began to take shape. By the early 1900s, private companies and local authorities had set up their own independent grids, but they built them as isolated islands. A generator in one town might supply power at one voltage, while the next town over used a completely different frequency. They were entirely incompatible. Because power couldn't travel far, it had to be made close to where it was used. Massive coal-fired stations were constructed right in the middle of cities, burning huge amounts of fuel just to light up a few surrounding streets. Without standardization, electricity couldn't scale. As long as it remained tethered to these fragmented local networks, it was destined to stay a luxury for a few neighborhoods rather than a utility for the entire country. The solution came in the form of alternating current, or AC. Paired with newly invented transformers, AC allowed power to be pushed to extremely high voltages, traveling over vast distances with minimal energy loss. With the flip of a switch, high-voltage energy could cross miles of landscape in a fraction of a second. This meant engineers no longer had to figure out how to squeeze a power plant into a crowded city block. The challenge shifted. Now they had to figure out how to link distant generating stations to towns miles away. Once electricity could physically travel across the map, it ceased to be a neighborhood product. Delivering it became a logistical challenge on a continental scale. To organize this expanding web, the government passed the Electricity Supply Act of 1926. It created the Central Electricity Board to force regional stations to standardize and interconnect. After World War II, the system was nationalized. The physical infrastructure expanded aggressively, with massive, centralized power stations built to push enormous amounts of energy into a newly unified national grid. Operating this system required a delicate balancing act. Control room engineers had to manually monitor dials and coordinate the flow of power across a vast web of transmission lines. By the mid-20th century, the grid in the UK operated as a single, fully synchronized machine. Every generator and every light bulb in the country beat to the exact same rhythm. That rhythm is a strict physical law. To maintain a steady frequency of 50 Hz, the exact amount of electricity being consumed across the country must be matched by the exact amount being generated every single second. This diagram shows how the grid protects itself using inertia. Traditional plants use massive high-speed turbines. Their physical momentum resists sudden changes. If a plant trips offline, the wheel keeps spinning, acting as a shock absorber, fighting voltage drops and buying operators time. These aren't small machines. They are colossal pieces of steel weighing hundreds of tons, physically locked into the frequency of the grid. For nearly a century, stability wasn't maintained by complex software or algorithms. It was guaranteed by the raw spinning mass of the grid's own generators. In 1990, Margaret Thatcher's government began breaking up this state-owned monopoly to introduce free market competition. Under new trading mechanisms, electricity was bought, sold, and traded by private companies as if it were a standard commodity like wheat or oil. But a severe friction exists here. Financial markets operate on future contracts and projected capacity over hours or days. The actual grid operates on the strict laws of physics, instantly. Layering a market over the power lines created a dangerous illusion. It masked the immense physical force required to keep the entire machine from collapsing in real time. To meet aggressive government decarbonization targets in the 21st century, the UK rapidly expanded its use of renewable energy. Vast offshore wind farms began replacing aging coal stations. At the same time, massive fields of solar panels were connected to the network. But these newer technologies operate in a completely different way. The hidden crisis is that solar panels and wind turbines don't have heavy, spinning masses directly synchronized to the grid's frequency. This side-by-side animation illustrates the difference. On the left, the traditional turbine provides intense physical momentum. On the right, the solar panel feeds power through a digital inverter. It provides clean electricity, but zero physical momentum. Retiring coal plants successfully slashes carbon emissions, but it simultaneously strips the grid of its natural shock absorbers. Removing that mass creates a severe, cascading physics problem. Today's system operators face a high-stress reality. Without that physical momentum to lean on, they have to manually balance a jittery, highly volatile network. It is like trying to balance a scale under a constant, unpredictable barrage of falling weights, fighting second by second to maintain equilibrium. Engineers are now deploying technology to simulate that missing inertia, building massive battery storage, instant demand side response, and using digital inverters to mimic the behavior of spinning turbines. Maintaining 50 Hz now depends on millisecond accurate digital response, replacing the physical momentum of coal with the speed of modern code. Fulfilling the goal of the ultimate machine has become a contest between the needs of the nation and the non-negotiable laws of physics.